Hello! In this presentation I'm going to talk about a load balancing scheme which assigns jobs using the number of jobs present in a queue combined with the time that the job at the head of the queue has already been receiving service. We refer to these policies as improved load balancing policies which use attained service time. So let's imagine that we are driving our car and we arrive at a toll gate with 6 lanes. We take a quick glance and we remember that there is a well-studied policy called the join shortest queue, which simply states that we should join the server with the least number of jobs in its queue. It seems like there is no reason not to use this policy. It has been proven to be an optimal load balancing policy, and it is commonly referred to as the golden standard. Looks like a pretty solid choice, right? We observe that there are 2 gates at which only one car is waiting. If we base ourselves on the join shortest queue policy, we simply pick one of these 2 gates at random. However, looking at the results regarding the join shortest queue policy more closely, we realize that there is an important assumption in these results. The optimality only holds in case of exponential job sizes. Indeed, the proof heavily relies on the memoryless property of the job size distribution. In real systems, job sizes are typically more variable. Therefore, a job which has been receiving service for a long time is probably a large job, and we should not queue up behind it. When jobs are processed in a first-come, first-served manner, it is not hard to keep track of the attained service time of the job currently being served. Using this attained service time to detect large jobs is the main objective of this work. For our toll gate, this means that we have a clock at each gate, and this clock indicates how long the car currently in front of the line has been receiving service. Comparing the clocks of the 2 gates, which have only one car waiting, we observe that the car at the purple queue has been receiving service for a much longer time. Therefore, we might suspect that it is a large job, and we join the blue queue. Of course, when there are too many lines to choose from, which might, for example, be the case in a cloud computing data center, we will not consider all gates, but we simply pick the gates at random and join the one which we expect will be able to serve us first. In this presentation, let us assume D is equal to 2. Therefore, we will join the queue which we expect to have the least amount of work out of these 2 selected queues. What information do we have? Well, we know that the first gate we picked has 2 cars waiting, and the car first in line has only been waiting for 1 tick of our clock. At the second gate, there is only 1 car, but that car has been receiving service for 5 ticks of our clock. Now we might wonder, which queue should we join? To answer this question, we define the function xi, which maps a tuple kl to a value in Rn. Here, Rn denotes an ordered version of the n-dimensional Euclidean space. We compare 2 elements in Rn by first comparing the value in the first component. If those are equal, we compare the values in the second component, and this continues on and on. Now, what are these k and l values? Well, the k value denotes the number of ticks on our clock we have passed. It is important to note that we use a discrete value to keep track of time. This simplifies the analysis significantly and barely impacts the results. When we pass this first tick, we have k equals 1, then k equals 2, k equals 3, and so on. L, on the other hand, denotes the number of cars in the queue. Therefore, using this notation, we can write down the situation of the previous slide as k equals 1 and L equals 2 in one queue, while we have K equals 5 and L equals 1 in the other queue. We then execute our function xi on both sides and assign the car to the queue for which xi evaluates to the smallest value. Simple, right? But the question remains, how do we define xi such that we can make a good decision? Well, to this end, let us consider a couple of different policies. First, for the classic shortest queue D policy, the incoming car would simply choose the queue which has the fewest number of cars in its queue. So therefore, we define xi of K and L as L. For this case, we find that the purple queue has the smallest xi value, so we would join the purple queue. Another policy, which was actually the one which made us start looking at this type of policies, is the shortest queue D policy, with runtime based tie breaking. For this policy, we look at the number of cars in each queue, and only if that number is equal, we will look at the number of ticks on our clock. A third policy is SQD with runtime exclusion. For this policy, we first look whether the car currently receiving service has been receiving service for longer than a preset amount of time, and exclude the queues for which this is the case. For our example, we set this threshold equal to 4, and we observe that the purple queue has indeed breached this threshold. Therefore, we will join the blue queue in this situation. Another really simple policy is the least attained service D policy, where we only look at the clock associated to the car at the head of the queue. As the clock on the blue queue has the smallest value, we would decide to assign the job to the blue queue. A policy which uses even less information is the runtime exclusion policy. For this policy, each queue only indicates whether or not its runtime exceeds a certain value. If we set this threshold equal to 5, we observe that both queues do not exceed this value. Therefore, the xi values are equal, and we assign the incoming car arbitrarily between these two queues. Last but not least, we consider the least expected workload D policy. For this policy, we compute the expected work left in the queue based on the runtime information. Of course, to be able to compute this value, we need to know the job size distribution. As our main objective in this work is to analyze load balancing policies which don't know anything about the job sizes, we will simply use the least expected workload D policy as an idealized version of the other policies we introduced. And our goal is to create policies which are able to approximate its performance without making use of the job size distribution. Well, these policies are all fine and dandy, but how does one go about analyzing these policies? As our main interest lies in models where there are many servers, we employ the queue at the cavity methodology to analyze these policies. That is, we single out one queue and assume all other queues behave in the same way. What this boils down to is having a potential arrival rate to this queue with rate lambda times d, given that the arrival rate to the dispatcher is lambda times the number of servers, and each potential arrival has a probability A of K and L to become an actual arrival. This A can easily be computed for each choice of xi. As we need to know the runtime of the job currently receiving service, we keep track of the age process and the queue length for a cavity queue. Let us start with an empty queue, so K and L are both equal to 0. We stay empty for some time, but then an arrival occurs. This increases the L value to 1, while K remains 0. This car is still waiting when the clock reaches the first tick, and at this point the K value changes to 1. While waiting, another arrival occurs. So now 2 cars are waiting, and we set L equal to 2. At the next clock tick, the same car is still receiving service, and we increment the K value to 2. Between clock tick 2 and 3, we find that the car finishes service and leaves the system. We therefore decrement the value of L to 1 and reset our timer to 0. You can imagine how this stochastic process can go on and on and on. We can define a discrete time Markov chain which keeps track of the value of our stochastic process at the time boundaries. For simplicity, let us assume that job sizes are exponential with mean 1. Let us denote by delta the time between 2 clock ticks, and then, starting in some state KL, there are essentially 2 possibilities. First, the car currently receiving service can simply remain in service for time delta. This way, we have a transition to the state K plus 1 L prime, where L prime is equal to L plus the number of cars which arrived in this time delta. Second, the car currently receiving service might leave the system before reaching the next clock tick. In this case, we reset the clock to 0, and the number of cars in the system equals L prime. But here, L prime equals the number of cars which were waiting behind the car that just left, plus the number of cars that arrived since the last time tick. This gives us a transition matrix P for a discrete time Markov chain. Computing this transition matrix P is easy if we know the distribution of K and L for the cavity queue. However, computing this distribution is exactly what we are trying to do. To solve this issue, we can use a fixed point iteration to find the stationary distribution. We first have some initial guess pi of K and L. From this, we can compute the probability that we assign a potential arrival to the cavity queue, which is in state KL. This allows one to compute the transition matrix P. From this transition matrix P, we can then compute the stationary distribution pi. If this stationary distribution is the same as the one we found in the previous step, well, then we have found the fixed point and we can stop the iteration. Otherwise, we again compute the assigned probabilities A of K and L and do another iteration. We have found that this method converges quickly and remains stable even for highly loaded systems. Of course, only considering exponential distributions is a bit restrictive, in particular because, as we have seen, the join the shortest queue policy is optimal for exponential distributions. Therefore, we generalized the analysis we presented here to phase-type distributions. In particular, this allows to analyze job sizes with a squared coefficient of variation which exceeds 1, which is typically the case in any realistic load balancing environment. To wrap up, we present one of the many numerical experiments we carried out in our work. We assume job sizes are hyper-exponentially distributed with balanced means and an SEV equal to 10. This basically means that there are both large and small jobs, which are both exponentially distributed, arriving to the system. And both types of jobs make up for 50% of the entire workload. We plotted the relative improvement in waiting time obtained from our policies compared to using the standard SQD policy. On the left, we consider policies which do not make use of any threshold value. We observe that there is a significant improvement in performance. In particular, our policies succeed fairly well in their goal of achieving the performance of the least expected workload D policy. On the right, we consider policies which do make use of a threshold value. In particular, we observe that the performance of the SQD-based policy, which combines runtime-based tie-breaking and runtime exclusion, is almost identical to that of the least expected workload policy. However, one issue that remains with our policies is the fact that the improvement of using them decays as the system load increases. This can be explained by the fact that as the system load increases to 100%, queues get longer and the information of the runtime of one job does not give us that much of an advantage. To overcome this issue, we should extend our methodology to scheduling policies which partially run jobs, which would ideally give us information on the runtime of all jobs which are currently in the queue. On that note, I would like to thank you for watching this presentation, and I hope to have inspired you to employ these methods in your own problems.